National Electrical Code Article 220 addresses branch circuits and feeders. Section 220.61 specifically discusses calculating the maximum net calculated load between the neutral and any one ungrounded conductor. Annex H provides informational notes related to the section. Resources like Electrical Calculations Simplified by Robert Williams, the NEC Training Manual by Charles A. Geyer, and Electrical Codes and Standards by Jones and Bartlett Learning offer further insights. To calculate the maximum net calculated load between the neutral and any one ungrounded conductor, use the following formula: maximum load equals unbalanced load plus neutral current times 2. Unbalanced load is the sum of the load currents on the ungrounded conductors that are not equal to the load current on the neutral conductor. Neutral current is the current flowing in the neutral conductor. Let's consider a three-phase, four-wire system as an example. Suppose phase A has a load current of 10 amps, phase B has 15 amps, and phase C has 20 amps. The neutral current, representing the unbalanced load, is 10 amps. To find the maximum load between phase and the neutral, we apply the formula: maximum load equals unbalanced load plus neutral current times 2. In this case, maximum load equals 10 amps plus 10 amps times 2, resulting in 30 amps. Therefore, the maximum net calculated load between phase and the neutral conductor is 30 amps. It's crucial to accurately determine unbalanced loads and neutral currents for safe and compliant electrical installations. The NEC provides guidelines and examples to ensure proper calculations. Remember, the unbalanced load is determined by the differences in current among the phase conductors. In a balanced system, the neutral current would be 0. However, in real-world scenarios, some imbalance is typical, leading to current flow in the neutral conductor. The formula maximum load equals unbalanced load plus neutral current times 2 helps account for this imbalance when determining the maximum load on any single-phase conductor relative to the neutral. Always refer to the latest edition of the NEC and consult with qualified electrical professionals for specific applications and interpretations of the code. Correctly applying Section 220.61 is essential for preventing overloads and ensuring the safety and reliability of electrical systems. Now, let's elaborate further on the concepts of unbalanced load and neutral current in a three-phase, four-wire system. The neutral conductor's role is to carry the unbalanced current resulting from unequal loads and the three phases. In a perfectly balanced system, where each phase carries the same amount of current, the neutral current would ideally be 0. However, in practical scenarios, residential, commercial, and industrial loads are rarely perfectly balanced. This imbalance creates a current flow through the neutral conductor. The magnitude of the neutral current depends on the degree of imbalance among the phase currents. For instance, if phase A carries 20 amps, phase B carries 15 amps, and phase C carries 10 amps, the neutral current will be the vector sum of these currents. In a purely resistive load scenario, you can approximate the neutral current by finding the arithmetic difference between the largest phase current and the sum of the other two phase currents. However, with inductive or capacitive loads, the phase angles between the currents become significant, and vector addition is necessary for accurate calculation. The NEC provides guidelines on how to calculate neutral loads based on the type of loads being served. Section 220.61b allows for demand factors to be applied to the neutral load calculation for certain types of loads such as electric ranges and dryers, as these loads are not expected to operate at their maximum rating continuously. Understanding the principles behind unbalanced loads and neutral currents is crucial for properly sizing conductors and overcurrent protection for feeders and services. Undersized neutral conductors can lead to overheating and potentially hazardous conditions. The NEC specifies minimum neutral conductor sizes based on the calculated neutral load. Additionally, it's important to consider the impact of harmonic currents on the neutral conductor. Nonlinear loads such as electronic devices and LED lighting can generate harmonic currents that add to the neutral current. These harmonic currents can significantly increase the neutral current even in systems that appear to be relatively balanced at the fundamental frequency of 60 Hz. To mitigate the effects of harmonic currents, it may be necessary to use oversized neutral conductors or harmonic filters. The NEC provides guidance on addressing harmonic currents in electrical systems. Now let's delve deeper into the practical implications of NEC section 220.61 and how it applies to real-world electrical installations. Consider a commercial building with a mix of lighting, receptacle outlets, and HVAC equipment. Accurately calculating the maximum net calculated load between the neutral and any one ungrounded conductor is essential for determining the appropriate size of the service entrance conductors and the main overcurrent protection device. The process involves several steps. Firstly, determine the connected load for each phase conductor. This includes lighting loads, receptacle loads, motor loads, and any other electrical equipment connected to the system. Secondly, apply demand factors to the connected loads based on the type of occupancy and the expected utilization of the equipment. Demand factors are reduction factors that account for the fact that not all loads will operate at their maximum rating simultaneously. The NEC provides tables of demand factors for various types of occupancies and equipment. Thirdly, calculate the unbalanced load on each phase conductor. This is the difference between the load on that phase and the average load on the other two phases. Fourthly, determine the neutral current. As mentioned earlier, the neutral current is the vector sum of the unbalanced currents on each phase. In many cases, you can approximate the neutral current by finding the arithmetic difference between the largest phase current and the sum of the other two phase currents. Fifthly, apply the formula maximum load equals unbalanced load plus neutral current times 2 to calculate the maximum net calculated load between the neutral and any one ungrounded conductor. This calculation provides the basis for sizing the neutral conductor and the service entrance conductors. It's important to note that the NEC allows for certain adjustments to the neutral load calculation based on the type of loads being served. For example, Section 220.61b permits a demand factor of 70% to be applied to the neutral load for household electric ranges and dryers. This is because these appliances are not expected to operate at their maximum rating continuously. In addition to the above steps, it's also crucial to consider the impact of future load growth. Electrical systems should be designed with sufficient capacity to accommodate anticipated increases in load. This may involve oversizing conductors and overcurrent protection devices to provide room for future expansion. Furthermore, it's essential to ensure that all electrical work is performed by qualified and licensed electricians in accordance with the NEC and local electrical codes. Proper installation and maintenance are critical for the safe and reliable operation of electrical systems. Now, let's examine some common mistakes to avoid when applying NEC section 220.61a. One common mistake is failing to accurately determine the connected load for each phase conductor. This can lead to undersized conductors and overcurrent protection devices, which can create a fire hazard. Another mistake is neglecting to apply demand factors appropriately. Using incorrect demand factors can result in inaccurate load calculations and potentially undersized electrical systems. A further mistake is failing to consider the impact of harmonic currents on the neutral conductor. Harmonic currents can significantly increase the neutral current, even in systems that appear to be relatively balanced. Another pitfall is neglecting to account for future load growth. Electrical systems should be designed with sufficient capacity to accommodate anticipated increases in load. Ignoring voltage drop is another issue. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. Finally, not consulting with qualified electrical professionals is a big mistake. Electrical work should always be performed by qualified and licensed electricians in accordance with the NEC and local electrical codes. To summarize, accurately calculating the maximum net calculated load between the neutral and any one ungrounded conductor is essential for the safe and reliable operation of electrical systems. By following the steps outlined in NEC section 220.61 and avoiding common mistakes, you can ensure that your electrical systems are properly sized and protected. Remember to always consult with qualified electrical professionals for specific applications and interpretations of the code. And also remember to regularly inspect and maintain your electrical systems to ensure their continued safe and reliable operation. Electrical safety is paramount, and it's crucial to take all necessary precautions to prevent electrical hazards. Now, to delve even deeper, let's consider the implications of different types of electrical systems and their impact on neutral current calculations. In a single-phase, three-wire system commonly found in residential applications, the neutral conductor carries the unbalanced current between the two hot legs. The neutral current is simply the difference between the current in each of the hot legs. In a three-phase, four-wire Y system, the neutral conductor carries the vector sum of the unbalanced currents from the three phases. As mentioned earlier, the neutral current is minimized when the loads are balanced across the three phases. In a three-phase, three-wire delta system, there is no neutral conductor. Therefore, neutral current calculations are not applicable. However, it's important to note that three-phase, three-wire delta systems may be susceptible to voltage imbalances if the loads are not evenly distributed across the three phases. In addition to the system type, the type of load also affects neutral current calculations. Linear loads, such as incandescent lighting and resistive heating, draw current that is sinusoidal and in phase with the voltage. Nonlinear loads, such as electronic devices and LED lighting, draw current that is non-sinusoidal and may contain harmonic components. Harmonic currents can significantly increase the neutral current even in systems that appear to be relatively balanced. The NEC provides guidance on addressing harmonic currents in electrical systems. It's also important to consider the impact of shared neutral conductors. In some cases, multiple circuits may share a common neutral conductor. This can reduce the amount of wiring required, but it also increases the load on the neutral conductor. The NEC specifies requirements for shared neutral conductors to ensure that they are adequately sized to carry the total neutral current. Furthermore, it's crucial to understand the difference between a grounded conductor and an equipment grounding conductor. The grounded conductor, also known as the neutral conductor, is intentionally grounded at the service entrance to provide a return path for fault current. The equipment grounding conductor provides a low impedance path for fault current to return to the source, tripping the overcurrent protection device and preventing electrical shock hazards. The equipment grounding conductor is not intended to carry normal operating current. It's important to keep the grounded conductor and the equipment grounding conductor separate to prevent unwanted current flow in the equipment grounding system. The NEC provides detailed requirements for grounding and bonding electrical systems. In conclusion, accurately calculating the maximum net calculated load between the neutral and any one ungrounded conductor requires a thorough understanding of electrical system types, load characteristics, and the NEC requirements for grounding and bonding. By following the guidelines outlined in the NEC and consulting with qualified electrical professionals, you can ensure the safe and reliable operation of your electrical systems.